the next review request was about electrolysis, which is just the breaking down of a compound by passing an electric current through it. So usually this is going to produce elements, pure elements. And I talked about two different kinds of electrolysis. The first was electrolysis of water. So this is really just one specific reaction, and it happens to be particularly important in a couple different settings. Is the only reason why I talk about this specifically, but it's one of the most common types of electrolysis that you come across in the world. Is passing an electric current through water to break it down into its elements of hydrogen and oxygen gas. So water is being both oxidized and reduced here. We have hydrogen starting at +1 in water and ending up at 0 in hydrogen. So that is our reduction reaction. And then oxygen is starting out at -2 and ending up at 0. So that is our oxidation process that's happening here. So we can see in our half reactions that water is the primary reactant at both the cathode and the anode. So water is being both reduced and oxidized to produce hydrogen and oxygen gases along with hydroxide and hydrogen ions at their respective electrodes. And so this is how this happens. So these half reactions are always the same for electrolysis of water because it is just one specific reaction. And so this always has a standard cell potential of -2.06 volts. So note that it is negative, which means this reaction is not thermodynamically favored, which is why we have to pass an electric current through water in order for this to happen. This is why water doesn't just spontaneously become hydrogen and oxygen. It prefers to stay as water unless we apply energy to break it down in this way. So because this is negative, that means this is not thermodynamically favored. And we need to apply enough voltage in order to overcome the negativeness of this reaction. So if you wanted to do this, you need to apply a voltage of at least 2.06 volts, that you need enough to overcome how disfavored this reaction is. So the applied voltage here needs to be really a little bit greater than 2.06 volts to get this reaction to happen. So the other example I gave was electrolysis of salts. So this is specifically most applicable to metal halides. So in a salt or in an ionic compound, generally the cation is a metal. The example that I gave is specific to the anion being a halogen. This can work for other anions, but it's a little bit more complicated. I'm mostly interested in situations where the anion is a halogen, so fluorine, chlorine, bromine, iodine. And in these cases, when you have your ionic compound, this is composed of a cation that is our metal and an anion that is our halogen. So some positively charged metal, it might be +1 or +2 or +3 or plus whatever charged, and the halogen is negative, your anion is negative. So what always happens in this case is that, again, we're producing elements. So similarly to water, where we produced hydrogen and oxygen, in this case, we're producing the metal and the halogen in their elemental form, which means in an oxidation state of 0. So our cation is always going to be reduced. Since it has a positive charge, to get to 0 oxidation state, it needs to gain electrons. So our cation is going to be reduced. It's going to gain electrons to get to 0 charge. Our anion has a negative charge. So in order to get to 0, it needs to lose electrons. So our anion is always going to be oxidized. In the case of a halogen specifically, they're all diatomic. So your reaction is going to look exactly like this, just with X substituted for whatever your halogen happens to be. So for example, in the electrolysis of magnesium fluoride. The magnesium is our metal, the fluoride is our halogen, is our anion. The magnesium is going to be reduced. Magnesium will gain 2 electrons to become pure magnesium, and the fluoride ions are going to be oxidized. They will lose electrons to become pure fluorine gas. And similarly to the water example, if you wanted to actually do this, you can figure out the voltage you need to apply just by finding the cell voltage. So our cell voltage here is negative 5.24 volts, which means that in order for this reaction to proceed, you would need to apply more than that. Your applied voltage must be greater than 5.24 volts to get this reaction to happen. We're overcoming the disfavoredness of this by applying external source of energy, so we need to make sure we have enough energy in order for that to happen.